Today I want to show you on a topic of sentence transformer, SBERT, how you can build your own question and answer system if you have a corporate body of knowledge that is, let's say, secret. It is more or less a Google functionality you can have if you do some semantic search on your millions of sentences. For example, on your customer experience, on your internal processes, on your patents, on whatever you have in-house. I will use this to show you the difference between an SBERT Bi-Encoder versus an SBERT CROSS-Encoder and why we will use both but at different points in our program. And also, as always, I will show you how to encode also paragraphs, because this was one of the questions of my viewer. So here we go. The first, we're here live in a Colab notebook. Just make sure that we have a GPU, because today we're gonna need a GPU. And then we're just gonna say, yeah, just run everything more or less. Run all. Let's go. Let's start. So at first, sentence transformers, we have to install our sentence transformers. And since I want to show you also the lexical search quality and how a semantic search improves over some lexical search, I have also to install the lexical search. So here we go. We're on a free Colab notebook. And here we go with all our dependencies that we need. Great. Then we have our sentence transformer, our classical Bi-Encoder. We load the CROSS-Encoder and we load the utility function from the sentence transformer. Just hope that a GPU is found. Beautiful. So let's start with an easy code example. I just want to show you the structure of our code before we implement it. So what we have a document. Here in this document, you can have millions of sentences, millions of paragraphs, 10,000 books, whatever you have, your document. And then we have a query. And the query is simple: how many people live in London? And to make it simple, we have just two sentences. And we want to know which of the two sentences contains the information. So how do we code this? At first, we need a sentence transformer model that has been pre-trained on the English language. Beautiful. Here we have it. We download it with this command from Hugging Face, and it's done. We have the model. Of course, then we have to encode with our model our query. Here, our query, and then we have to encode, of course, the document. So we encode the query in the document with the same transformer model. Great. If we do this with the Bi-Encoder, you know that we will get a vector and a high-dimensional vector space. To compare those two vectors, we simply use a cosine similarity, and this has been taken care of. In the utility package, we have a dots underscore score. So where we have our query embedding, the document embedding, and they just tell us, okay, let's do the calculation. Then we combine it and we sort it, and you will get the result. So we download everything from Hugging Face, and the result you will get are these two lines of code. We have two sentences, and with a probability of 0.9, so a very high probability, you see that the sentence, how many people live in London? The correct answer is around 10 million people live in London. And the second answer, the second best, is only with a probability of 0.5, London is known for whatever. So great. This is the idea that we're going to implement it now. A data set. We take Wikipedia. We take a simple version of Wikipedia because we are working here on a free RAM, a free Colab notebook, and we have limited RAM and GPU RAM. So yeah, that looks great. Maybe we can. Okay, yes, okay, system RAM and GPU, no, for the moment, no, we don't need this. So let's do this. So at first you go and you say, okay, let's load the line. Now, what we do here, because we are limited at RAM, I just want to show you, you can add only the very first paragraph. So you see here, we go with the very first paragraph. In this paragraph, we have two sentences, three sentences. I'll show you in a second. We call it a passage. You can go, of course, for all paragraphs in Wikipedia, then you just ignore this 0 component here, and you go with data paragraphs. So if I do just go with the first paragraph in Wikipedia for each topic, I have about 169,000 different passages. How does a passage look like? Now here you see passage number 0. We have sentence 1 and we have sentence 2. This is it. Now the second passage you can see is a little bit more complicated. We have 1, 2, 3, 4 sentences. 4 sentences, yeah, that constitutes as a real paragraph of text. And this is how we're gonna encode it for some semantic search in SBERT then. So what is the easiest? The easiest is lexical search. You have no semantic information. We use here something called best matching 25. This is from the 1980s, and it is more or less, if you notice, a bag of word retrieval function that ranks document based on the query terms, regardless of their proximities. This is already done for us. There is here, we just download this functionality, we strip it here of the punctuation, we take care about the English stop words, you know about them, and we get the result. So we have our lexical search. I'll show you in a minute what's the result. Now the interesting part is now that we go here for the semantic search. And at first we use a Bi-Encoder. Since you remember we have 169,000 paragraphs we want to encode, let's go with a Bi-Encoder, because a Bi-Encoder is very fast. It is not so precise as a CROSS-Encoder, but a Bi-Encoder is fast. So of course, we use here the code from the GitHub repo UKP lab sentence transformers, and here I leave you all the documentation if you want to have a look at this. Here's the preprint, the relative preprint, and of course there's a beautiful documentation at sbert.net. Please go there and have a look at their detailed description. But let's go here with our path forward. So here we go now with our Bi-Encoder to encode all passages. So we say sentence transformers, and we download a specific model, a question and answer model that has been pre-trained for us beautifully. And then you have to take care of this particular system has only been trained on 256 BERT tokens. So careful, you only have 256 not words, but words that are not in your dictionary will be truncated. So take care that if you use a model that has only been trained on 256, although BERT can do 512 tokens, that you choose the right maximum sequence length. And then the number of passages we want to retrieve with this BERT encoder is, let's say, 128. So how we do this? Easy. We say Bi-Encoder. This is what we just loaded here from Hugging Face. We say .encode. Then we give them our passages, our text. We convert to a tensor, show progress bar. And as you can see here, after 1 minute and 49 seconds, we have done it on the GPU. And what you will get back is the embedding. This is a vector embedding. So this means you get a tensor. And this tensor has about 169,000 rows. And each row has about 384 columns, which define a coordinate system in a 384-dimensional vector space. Here we see this here. If I say, hey, show me the shape of this PyTorch tensor, it gives me 169,000 rows and 384 data columns. Great. Now I just have to convert this. I want to show you this in a Panda data frame, so I just convert it in a Panda just to make sure we get the same amount of data. I just save it to a CSV file. Beautiful. And now we are here at our search functionality. So we have two parts. The first is the lexical part. This is not semantic. This is just the appearance of words. Beautiful. And then we have here our semantic search. So we do the same as I showed you in the demo. We say now, okay, we have a question. We have to encode our query, our question, with our SBERT Bi-Encoder. and we put it on the GPU, on our CUDA cores. And then we have in the utility function of SBERT, we have the semantic search function, where we just provide the question embedding, the corpus embedding, the maximum number of returns we want. And since this is done so that you have multiple parallel questions, we just want to get the first question, because we only will have one question for this demonstration, and then show me the top 3. And this is, if we run this, just show you in real time, let's run this, that you see that this is really the code. So my input question was, as I said here, what is the capital of the United States? Should be easy for Wikipedia. So this is my input. Now, a lexical search gives me this, and there's not the correct answer. Now, if you use now a semantic search, a Bi-Encoder, it will reveal this. So it is, the United States capital is the building, and then another text. Also not the correct answer. So we need to further improve our question and answer system built on neither lexical nor the pure Bi-Encoder. We need another powerful instrument. Let me show you. So my query was this. What I get back is now my corpus ID. Remember, from these 169,000 paragraphs, it computes a score, a matching score, to my query from the corpus for all 169,000 corpus ID elements. And the score is, of course, ranked accordingly. So you see here we go. As you notice that we are not really close to 1 to a high probability, but we are somewhere here 0.5, 0.4, so we have to improve. Just give me a sec. So yeah, I want to show you also a data visualization you can use. So I need to do a little bit of data handling for my visualization. Sorry for this, just forget about it. It's not important for SBERT. I just construct here a Panda data frame for the pure visualization task. Yeah, never mind at all. I save my Panda data frame to a file. Beautiful. This is how it looks. And here we go. So now what we have, and as I can show you here, we have 120 of our retrieved SBERT Bi-encodings, our embedding in a 384-dimensional vector space. And as you can see here, this for this paragraph set with the ID 77,000, blah, 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 we have here 384-dimensional coordinates. Beautiful. Let's just show you. Okay. Where are we here? 361. Okay. So 384 dimension. And then I have here just the text element of what is the text within this passage. Beautiful. So now we have to reduce, because I want to have a 3-dimensional representation. So I have to go from 384 dimension, where the information, the semantic information, is encoded to 3 dimension. And UMAP is beautiful, so pip install UMAP learn. We install all dependencies. We import UMAP. And just to show you, to reduce the data from 384 dim to 3 dim, I take the simplest possible approach. No tuning, no fine tuning, nothing. Here you can play for hours if you want, but it's just for demonstration. So I say, hey, look at the topological neighbors that are only 5 away. The minimum distance I've chosen, you can also take a finer gradation. And the number of components, this is a 3-dimensional representation I'm looking for. Beautiful. So then we apply this to our data set. So we will say umap.fit_transform, and then I have here my 384-dimensional vector embedding. Beautiful. And I say, let's reduce it to 3. So what I get out, as you can see here, is I get now a vector representation of 121 different different rows with only 3 columns. Beautiful. And now what I say, and you know this, I say, hey, pip install Plotly in my Colab notebook. And here I go. And I say X is not X coordinate, Y is the Y coordinate, and Z is the Z coordinate, and beautiful. And now I have two additional information. I want to have now also my query, because my query is also in a vector embedding. I want to code my query in a yellow sphere so that I can really see my query, my data dot in 3D. And then I know the answer. And the correct answer is encoded here in this specific area that I checked personally. And I'm going to say I want to have a blue sphere. So let's do this. Let's run this command that you see it's live. And I call it a question and answer SBERT Bi-Encoder. And here we go. So what we have here, the dots give us all the answers we get from the Bi-Encoder. And immediately you see that some of them are outside of a scope and you have a real nice clustering. Although we do not have a UMAP full-fledged, you see that the clustering effect is really clear. We have here more or less our interesting data. Now, as you can see here, this dot here, this middle of my blue sphere is exactly my question. From my question and answer, what is the capital of the United States? And as you can see here, the answer is here. This dot here is Washington, D.C. So I have now to choose the size of my sphere in a way that the answer, the correct answer that we did not find with a pure Bi-Encoder, is within now this yellow sphere. So this visualization should show you, you have to choose now for the next step, because as I showed you in the top three answers that we get with an SBERT Bi-Encoder, that blue was not in. And now you see why in this very simple 3D presentation, because if you have here the middle point of our sphere, the three closest are not the answer in a blue sphere. So we have to have we have to expand our solution space that we include the correct answer. So let's do this. So now we apply a SBERT CROSS-Encoder for a more detailed semantic search that we get back from our Bi-Encoder, and our Bi-Encoder limited set of only 120 solution of only 120 data points that you can see here. I also take those yellow with me. Okay, you could neglect it, but I take here all the different points because I want to make sure here, if this is my particular point, I want to have all those 120 possible solutions. And then I want to apply now the CROSS-Encoder for the detailed semantic search within this limited data set. Now, easy. Again, lexical search, but you have the comparison. Semantic search, I showed you already. And this is now the new piece of code. So what we do is easy. We do exactly the same. We take our query. We take now our data, our response that we get from the Bi-Encoder. We say this is it. And then we have a CROSS-Encoder, and the CROSS-Encoder should be here. The CROSS-Encoder we download also from Hugging Face. It has already been pre-trained on the English language. And we have here MS Marker, Mini LM, and we have already version 2. Go to Hugging Face, give in this as a model description, and you will get all the details, how it has been trained, when it has been trained, when was the update, everything. We just need the CROSS-Encoder, a pre-trained model. Beautiful. And now we say here in our number 3, where's our number 3? And here's our number 3. We say now CROSS-Encoder.predict. Exactly our set of query and 120 answers. Here we go. We print it out, we rank it, and now we get the top 3 hits from our CROSS-Encoder. Beautiful. Do this, and now let's run the query where we have now all 3 components. The lexical search. Here's our lexical search. Then we have the pure Bi-Encoder that scans through all 100,000, 200,000, 500,000 paragraphs of text. And then we take just a subset of our Bi-Encoder 120 closest answers, and then we apply a CROSS-Encoder to re-rank our hits. And here you see exactly, given our question, what is the capital of the United States? With our CROSS-Encoder, we immediately get back on position number 1, the correct answer, Washington, D.C. So as you can see here also, in the numerical fit parameter, we have close to 9. So this is really, you see the second answer as 3, 3. So with a high probability, the system tells us with a pre-trained CROSS-Encoder on the English language on this particular data set of Wikipedia that Washington, D.C. is the right answer, and you know, this is it. You can, of course, have other questions just for a demonstration. I'll show you the next one. What is the best orchestra in the world? The top Lexical Search will give you here the British Broadcasting Corporation, the Symphony Orchestra, or the whatever. You know, of course, since you know I'm from Austria, the Bi-Encoder reveals here already, oh yeah, number 1 and number 2, yes, based in Vienna, Austria. Yeah, this is of course the right answer. You know that this is the right answer. And unfortunately, if we do a detailed search with a CROSS-Encoder, it tells us that they think that the London Symphony Orchestra is one of the most famous, but not the best, just famous, and of course Vienna Philharmonic Orchestra. Yes, this is the right answer. So you see 5.9 and 5.79. Oh, this is really close. So here you get an idea why we apply in a Q&A system at first a Bi-Encoder from SBERT, and then on a limited solution set we apply a CROSS-Encoder to really get the fine-tuning of the SBERT model, to really get the full power out of the system. But we cannot apply a CROSS-Encoder on millions of entries. Time would be going up as always. So solution step is Bi-Encoder and then CROSS-Encoder. I hope you enjoyed this video. I hope also that the visualization I tried to include here, now that we know how to do beautiful 3D visualization, that you see why we have to choose certain spheres, solution spheres, when we apply here CROSS-Encoder with a given answer. And as you can see, you can scroll here through and you get all the different answers that we are looking for. I say thank you. I hope you enjoyed it a little bit. You provided some information for you. And if you're interested in SBERT and to build your own corporate information system, maybe on a secret body of knowledge that you have protected within your company, or you're working for somebody, you can build your own Google if you want with a simple transformer model. And I showed you how to use the SBERT Sentence Transformer, at first the Bi-Encoder and then fine-tuning a CROSS-Encoder. If you want to read more about it, please refer to the documentation that I showed you. And this is here, I recommend sbert.net. I say thank you, and I see you in the next video.